Okay, shall we start, guys?
Yes, sir.
Yes, sir.
Yeah. So tetrahedral complex, we have this kind of structure, right? The ligands are present at the corner of the tetrahedral. We are going to see the splitting in orbitals, how the orbital splits in tetrahedral complex. Okay. So obviously you see the bond angle is 109 degree 28 minutes. Along any of these lines, we cannot assume any axis, right? But if axis is there, it will be something like this. It is present at a 90 degree like this. Suppose this is the axis, we have x, y. Just a rough diagram I am trying to draw, right, at 90 degree. So obviously what we can say, the ligands are approaching the metal. It is not along the axis, but it is in between the axis, right? In between the axis, you see. So obviously the non-axial orbital that you have, in this case, the non-axial orbital experience more repulsion, and hence it goes to the higher energy level. So if you look at the splitting in this orbital, the splitting is like this. See, CFT tetrahedral. It's just the ulta, reverse of octahedral complex. All the the axis is same, y-axis and x-axis. The T2G orbital goes to the higher energy level, and EG comes down to the lower energy level. Okay, everything is same, the axis and all, everything is same. And in this, again, if you have to distribute the electron, all those things you have to consider: field, strong field, unstable, right? Energy gap, everything. But those things are not there. Okay, you don't have to think about all this. If it is there, you have to consider like that. Now the splitting here is given as delta T. You see, T stands for tetrahedral. This is delta T. Okay, and there is a relation of delta O and delta T, and this relation is established experimentally. And the relation is delta T for tetrahedral is equals to 4 by 9 times of delta O. 4 by 9 times of delta O. This is experimentally determined. No proof, nothing. Many times they have asked this question. Right? So you must have to keep this in mind. From this only you can understand easily that delta T is less than delta. This is also, you can conclude from this.
So,
yes, tell me.
so this relation is for a particular pair of a particular complex.
Yeah.
So, but then how will one complex have octahedral and tetrahedral?
See, if it forms like, see, we can have K3 FeCN6 forms, K4 FeCN6 forms, right? Means two different kinds of arrangement. If it is there, then we have this kind of relation, tetrahedral complex, and if the different ligands, obviously, if the ligands are so different in the two different molecules, then we cannot compare these two, right? Because the different molecules are there. But yes, if you have some compounds like, for example, if I take an example, Fe F4, we can have different charge on this. No, on the complex ion, we can have different charge on this. With this, or Fe F6.
Okay.
So this charge may be differ on this, and then it can show the the complex, whether it is tetrahedral, octahedral, or whatever.
Okay, so got it.
Okay. So this is tetrahedral complex. Right? Every other thing is same. You don't have to think much about it, like because we have discussed a lot of things in octahedral complex. Those things we can apply here also, but that is not there in your syllabus, right? So just let it be. Now, if you have a square planar complex, then how the orbitals split? Did you draw this, all of you?
So one second.
So what is that on the top, non-axial orbital?
Where
So on the
non-axial
top, right?
orbital experience more repulsion.
Okay, sir.
Done.
Yes.
Okay. Now square planar. Okay, in a square planar, obviously you see the structure is this, and since it is square planar, so all the ligands are along this line, right? There is no ligands along DZ square orbital. Metal we have here. So one thing is sure that the orbital dx square y square experience the maximum repulsion, right? Like in octahedral, the repulsion of dx square y square and dz square is same, but here dz square won't have similar repulsion like dx square y square we have. So the T2G orbital also splits into two parts. Sorry, EG orbital also splits into two parts, and T2G also splits into two parts because of the different repulsion in different orbitals. So let me show you the splitting here, then you will understand it, how it happens. So square pyramidal, the splitting is like this. See what happens here, since the ligands is approaching the metal along this two orbital dx square y square. So this one obviously have the maximum repulsion. So this is the maximum energy, right? In between these two, if you compare dxy and dz square, right? So dxy orbital is in xy plane, and ligands are approaching along xy plane only. That's why the dxy will have more repulsion than dz square. Dz square and dxz yz, you see, obviously it is in xz plane and it is in yz plane, right? Perpendicular to xy plane. But dz square, you know, this orbital has an electron cloud in the xy plane. Yes or no? Yes, this is dz square. It has the electron cloud in the xy plane, and that's why this orbital experience slightly more repulsion than dxz and dyz, right? Hence the splitting is this. They haven't asked question on all this, but yes, you should know the at least the order of this. Which orbital should have the maximum, will have the maximum energy, which has the minimum energy. This thing at least. Done.
1 minute.
Z ligands along this line, we do not have ligands. Right, in comparison to the octahedral complex. Done?
Yes, sir.
Okay. Now the first part of this chapter, that is coordination compound, is almost done. We are left with only last, part of it, the first part. Then after this, we'll start with isomerism in coordination compound, the last part of this chapter. So we are left with only organometallic compound. Organometallic compound, if you remember, we have discussed it in organic chemistry also. When we are doing Grignard reagent, I said that this is an organometallic compound. Organometallic compounds are those compounds in which we have the bond between carbon and metal. Okay, so there are three types of organometallic compound. Right, RMGX is one type. We have a specific name for that. I'll tell you what. So first of all, write down. It's just a theory. You just need to know a few structures and few names. That is it. Nothing much you have to keep in mind here. Write down. These are the compounds in which carbon metal bond is present. These are the compounds in which carbon metal bond is present. This is classified into three categories. Okay, carbon metal bond is present, classified into three categories. The first type we have sigma bonded complex. Sigma bonded complex. Okay, simple. In this type of complex, there is a sigma bond between the carbon and the metal. Okay, so carbon and metal joined with a sigma bond. Carbon metal are attached with a sigma bond, and hence we call it a sigma bonded complex. Sigma bond. The example we have RMGX Grignard reagent. We can have Al2 CH3 6. This is also sigma bonded complex, right? Electron deficient AlCH3 dimerizes. This is the example we have. Next type we have pi bonded complex. In pi bonded complex, obviously pi electrons are involved with metal. Okay, pi electrons are involved with metal. These are the complex. These are the complex in which the metal ion is bonded with pi electrons, and we can have pi electrons of alkene, benzene, alkyne, and any other molecules. Okay, pi electron clouds. Pi electron clouds. For example, you see these structures that I'm going to draw. These structures are important. Okay, they have asked these things in the exam. Okay, you see this. We have a 5-membered ring. 5-membered ring. Metal is iron, and this side we have another 5-membered ring. This pi electron cloud, it donates to this metal. Just a second. This is the bonding we have. Okay, this compound we call it as ferrocene. All these names you have to memorize. Okay, ferrocene. We also represent this as metal is iron. So we write here this one. See this? We write here Fe, then a Greek letter eta, ETA. We write eta dash. For one molecule, we have C5H5, the structure of the ligand. This is the ligand we have. C5H5, we have 2 times, so hold 2. And we'll write a number on the top of it, eta. That number is the number of carbon atom in the ligand. Okay, that is 5 carbon, so 5 we have here. Once in NEET, they have asked this question. They have given the structure and eta to the power x they have written. X, eta to the power x, and the question was, what is the value of x? Okay, so x here, or the number here, is the number of carbon atom in the ligand. Carbon atom you can say, or number of atoms in the ligand. Eta to the power 5, the name is ferrocene, representation is this. One more example we have, in fact 2 we have. Pi electrons of benzene, you see this. With chromium, and this attached with benzene. Okay, this we call it as dibenzene chromium. Dibenzene chromium, and the representation of this is Cr for chromium, eta to the power 6, C6, H6, 2. Okay, another example you see. We have a cyclic compound, platinum. Here we have chlorine, chlorine, chlorine. Metal is this, and this metal, the ligand, the fourth ligand is this one, carbon with 2 hydrogens, CH2. This is the carbon with 2 hydrogens, CH2. Okay. This is the complex part, and K plus we have. Okay. The name of this compound is Jesus salt. G salt, we also call it as. Okay, important. And the representation is the cation first, metal is platinum, Cl3, 3 chlorine atom, and this is eta, C2H4. This is it. So the pi bonded complex that you have, or the ligands which pi electrons contains, here you see Cl3, 3 ligands I have written simply. But the pi electron ligands we used to represent with this eta. Done? Okay. Third type of organometallic compound we have, and we call it as sigma and pi bonded complex. Sigma and pi bonded complex. Write down, these are the complex. These are the complex in which the bond between the metal and carbonyl group the bond between the metal and carbonyl group is present. Okay. So this is basically the metal carbonyl compound. In that only we have sigma and pi bonded complex there. Right? The oxidation state of the metal is 0. Right? This one is also important. On this also they have asked question many times. Okay. Right, on the oxidation state of the metal is 0. For example, you see NiCO4, since the ligand is neutral, so oxidation state is 0. CrCO6, metal carbonyl compound. Okay, in this type of compound only the sigma and pi bonded complex we call it. Okay, now the important point here is, I'll give you one note here. On this note, they have asked question many times in the exam. They generally ask which statement is correct regarding this kind of complex, like this. Okay, so in this note everything is there, you can understand it. I'll explain the note also later on once you finish it. Write down first, in this type of compound, metal and carbon atom in this type of compound, metal and carbon atom contains both sigma and pi character. Both sigma and pi character. Next line. Sigma bond is formed by the donation of lone pair of electron by the donation of lone pair of electrons of carbon lone pair of electrons of carbon to the vacant orbital, lone pair of electrons of carbon to the vacant orbital of metal, carbon to the vacant orbital of metal, and pi bond forms due to the back bonding and pi bond forms due to the back bonding of a fully filled d orbital to the vacant anti-bonding pi orbital of carbonyl group, to the vacant anti-bonding pi orbital to the vacant anti-bonding pi orbital of the carbonyl group.
Excuse me, sir.
Yes.
Sir, if a bond is being formed by the donation of electrons from carbon, then how is it a sigma bond? I mean, isn't it a coordinate bond then?
I'll explain. Did you copy this,
Yes.
Kerry?
Yes, sir.
Okay. So you see how it happens. First of all, you see this carbonyl group CO. How many electrons it has? 8 plus 6. We have 14 electrons, right? And for 14 electrons, if you draw the configuration according to MOT, molecular orbital theory, this would be sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2py, pi 2pz, sigma 2px, then pi star 2py, pi star 2pz, then sigma star 2px. This is for n less than equal to 14. If it is greater than 14, 14 to 20, then we have to interchange this. This will come over here and this 2 will come this side. This 2 we need to interchange. That is the only difference we have. Okay. Now, since we have 14 electrons, if you fill this 14 electrons, 2, 4, 6, 8, 9, 10, 11, 12, 14. So you see this pi, first of all, it starts, these are anti-bonding orbitals, right? Anti-bonding pi orbitals, which is vacant. Anti-bonding pi orbitals. So the metal that donates electron in back bonding, it donates electron into the pi star orbital, anti-bonding orbital. So if you look at the metal, which has the 5 electron, suppose I'm just rough diagram I'm drawing. Suppose one orbital is this, another orbital is this, and This is metal, right? One electron pair of metal which involves in back bonding, and carbon monoxide is this. Sorry, carbonyl group, carbon monoxide. The C triple bond O. Oxygen has one lone pair, and the carbon has one lone pair in its orbital. One lone pair of carbon, and this is the pi star orbital, anti-bonding orbital of carbon. Okay, so the sigma bond forms. For that, carbon donates its lone pair of electron into the vacant orbital of the metal. This forms a sigma bond. And pi bond forms since it is a pi star anti-bonding orbital. So from the metal, the d electron donates its pair of electron into the vacant anti-bonding pi orbitals of this carbonyl group. Okay, this forms the pi bond. So pi bond forms by the back bonding of pair of electron of metal into with the anti-bonding pi orbitals of carbon, carbonyl group, and sigma bond forms by the donation of lone pair of electrons of carbon to the vacant orbital of metal. So this is we have in carbonyl compound sigma pi complex. Yes, you tell me now.
Yes, sir. Got it, sir.
So both are actually coordinate bonds only.
Yes.
Okay.
Coordinate bond are like, no, it's a type of covalent bond only, no?
Yes, sir.
Right. So yes. Why they have done this changes here? Because the most of the compounds which involves coordinate and covalent bond, they have the similar properties. That's why they have merged the two.
Yes.
Got it? So this, the note that I have given you, on that they have asked question many times in JEE also. Which statement is correct or which statement is, incorrect, like that. So all these, whatever we have done, there are so many questions possible. Like small points, when it is high spin complex, when it is low spin complex. For low spin complex, what is the nature of the ligand, weak ligand or a strong ligand? All these kind of questions they have asked many times. Okay, so this is the first part of this, chapter. The second part, which is the last part of this chapter, we have, that is nothing but the isomerism in coordination compound. Okay, so coordination compound shows both kind of isomerism, structural and stereo. Stereo part is the only which is important, right? But they have asked question from structural also. In stereo, we have geometrical as well as optical isomerism possible, right? So we'll start with this. Let's write down isomerism in coordination compound.
Sir, I had one small doubt in the previous. Sir, why can't the oxidation number not be 0?
Which one? Where?
For the metal carbonyl bond.
Oxidation is
pi complex. Yes, sir, I'm asking why can't it be 0? I mean, why can it be, why does it have to be only 0?
Why it is, see, NiCO, I have given you the example, NiCO4, correct? This is a complex.
Yes.
Metal carbonyl compound we have, CrCO6. There's no charge, you see. This ligand is neutral. There's no charge on the complex. It is stable also. Nickel, how many electrons? What is the atomic number of nickel?
28, yes.
8, 4 ligands, right? 4 into 2, 8 electrons it provides. 28 plus 8, 36. It is stable. Why, without any charge only it is stable. Hence it is not.
Sir, but what if it's something else? Like you had given examples that, sir, like VCO6 or something.
That is different. We have metal carbonyl compounds plus some other ligands also present. No?
Yes, sir.
So that is a different case. Here we have metal and carbonyl compound.
Okay, sir.
That's why you see I have given the examples of this tool.
Yes, sir. Yes.
Okay. Yeah. So isomerism in coordination compound. Fine. So two types of isomerism. I'm just not going into detail of all this because you know what is isomerism and all. So two types of isomerism it shows: structural and stereo. Right. So first we'll see structural isomerism. Here also we have certain definitions and then examples of it. Stereoisomerism, we have to see how to draw the different isomers and how to find out the drawn structure is different from the other structure. There we have to understand a bit. But here just we have definitions and then examples of that, like we had in the isomerism chapter. Okay. So the first types of structural isomerism we call it as ionization isomerism. Definition, write down. Very simple definition. On ionization, it gives different ions, are called ionization isomers. Basic thing is same, like the structural formula must be same. Without that, we cannot even imagine of isomerism, right? So the formula must be same, the molecular formula of the compound, right? If on ionization they give different ions, then they call it ionization isomerism. Okay, write down. These isomers have same molecular formula. These isomers have same molecular formula and produces when the ligands and the outer atoms, means outside the coordination sphere, the ligands and the outer atoms are interchanged. For example, we have CONH3 4 Cl2Br. Okay. On ionization, it gives Br minus and this plus. If I write down the another molecule of this, which is CH3NH3 4 ClBr and one chlorine outside. So both has the same molecular formula, but on ionization they give different ions, and hence these are ionization isomers. Okay. Second type is hydrate isomerism. Obviously, this phenomenon is isomerism. Okay. Hydrate, or we also call it as solvent isomerism. Write down, this is a special type of ionization isomerism. This is a special type of ionization isomerism in which the water molecules are involved. In which water molecules are involved. CrH2O, 6 Cl3 outside present, and CrH2O, 5 Cl2 dot H2. So water molecule is present outside. Okay, so this is hydrate isomerism. Okay, or solvent isomerism.
Sir, could you go back just a minute? Yes, sir. Thank you, sir.
Okay, next. Next is linkage isomerism. Third one. This is possible with ambidentate ligand. Simply the linkage is different. Okay, write down. This type of isomerism is theoretically possible in any coordination compound containing an ambidentate ligand. Containing an ambidentate ligand. Okay. Example, very simple one. CONH3, 5NO2, 2 plus, and CONH3, 5ONO, 2 plus. Linkage isomerism. Oxygen is the donor atom, nitrogen is the donor atom. Fourth one, coordination isomerism. Coordination isomerism. Write down. The compound which has both cationic and anionic complex ions, the compound which has both cationic and anionic complex ions shows this type of isomerism. And this is obtained by these isomers are obtained by the interchange of ligand in both ions. Interchange of ligand in both ions. Okay. For example, we have CuNH3 4 PtCl4. This is the complex we have. Could you tell me the charge on this complex and this complex?
Sir,
Plus one,
C1
minus two.
plus 2 plus 2 minus 2.
Plus 2 and minus 2, because the total charge is 4, will divide equally plus 2 minus 2. Now, if you write down the coordination isomers of this, what you do, you just exchange the ions here, the ligands, sorry. Cl here and PtCl3 NH3. This is the another molecule we have. Here we have plus 1 charge and here we have minus 1 charge. Total charge will be plus 2 and minus 2 always. Okay. Further, if you write down CuNH3 2Cl2 PtCl2 NH3 CuNH3 Cl3 PtCl NH3 whole price. CuCl4 and PT NH3 4. Okay, so here the charge would be 0 and 0. 0, 0. This further here the charge would be minus 1 and here it would be plus 1. Here it is minus 2 and plus 2, like this we have the charge. Okay, all these possible combination we can draw, but out of this 5 combination, this one is not possible. This one is not possible. Whatever. Wait. Why this one is not possible, I'll tell you. Because the charge on the ions is 0. And there is no attraction between the two part of it, cation and anion. If the charge is 0, this is also independent, this is also independent. There's no attraction. So this as a whole, it's not a compound now, right? Because there is no interaction between the two parts here. That's why this we cannot consider. This is not the possible isomers. The answer for this one, 1, 2, 3, 4 isomers are possible. Got it? Do it fast. We'll write down one more. Last one.
Sir, in the actual compound, will they exist as mixtures?
No, we are just drawing it. Like, if you exchange the actual compound is this only. Whatever is written, that will be the compound. It won't exchange. It is not like isomers, it's not like resonance that things get, changes from here and there. Shifting of, ligands is not possible on its own. But if you write down the structure like this, it is possible. Right? We're talking about isomers, so we can write down the molecules.
Yes, sir. Yes, sir.
So one last type here, we'll finish it. Write down next one. That is polymerization isomerism. Polymerization isomerism. Write down. This type of isomerism exists in compounds having same stoichiometric composition, but different molecular composition. Same stoichiometric composition, but different molecular composition. Same stoichiometric composition, but different molecular composition. PtNH3Cl2, and you see this one, PtNH3 4 complex part, and PtCl4 complex part. This too, if you see the ratio of platinum, NH3 and Cl in the two compounds, it is 1:2:2, and here it is 2:4:4, which eventually comes out to be 1:2:2. So this kind of ratio, if it is same, different molecular formula but stoichiometric composition is same, so this compound is our polymerization isomers of. Did you get it?
Yes, sir.
Okay. So this is it for structural isomerism. Here we have only definitions and then the examples of it. Next class we'll finish this chapter. We'll do stereoisomerism. That is very important. We'll finish this and we'll start another chapter. Okay. So center module you can solve. I'll share tomorrow. I'll share one PDF also on this, which you can try. Okay. Yeah. Anything else, guys? Chalo, ठीक है. Okay. Thank you, guys. Take care.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.
Thanks, sir. Happy Teachers Day, sir.
Thank you, sir.